All right, so now let's talk about the shapes of molecules. So, atomic orbitals are solutions to electron wave equations in 3D space. So what we have down here is three different examples of orbitals. So 1s, 2s, and 2p orbital, in this case 2pz. So what you notice here is that there are, positive and negative indications for some of these orbitals. And what this means, right, it's not an indication of positive or negative charge, it is just a phase, right? And for the most part, and we can spend lots of time talking about this, talking about wave functions, talking about more in-depth quantum solutions to these atomic orbitals, but sort of beyond the scope of the class in that regard. We will talk about it briefly, but we won't go into too much detail. But in general, right, the space in an atomic orbital is determined by the probability of finding an electron in that location. Right, so in the case of the p orbitals, right, there's a sort of plane in between the lobes, right, the positive and negative phase lobes, where there is no probability of finding an electron, right? So that's what it's called a node. And right, so like I just said, positive and negative don't indicate charge, but they signify wave function. And this positive and negative phases matter when these atomic orbitals come together to form bonds, right? As it signifies whether you have constructive overlap, meaning you're forming a bond, or destructive overlap, where the possibility of finding an electron is zero. And again, we can spend a lot of time talking about this, but it's better suited for a different class like physical chemistry. And so, as I said, nodes always occur when a wave function changes from positive to negative or vice versa. Again, like we can see here with this p orbital. So molecular orbitals are when two atomic orbitals overlap to make a bond. And bonds are signified by the in-phase overlap of these atomic orbitals. So overlap of atomic orbitals give rise to two different types of bonds: sigma bonds, or single bonds, and pi bonds, or double bonds, as you've probably more commonly heard it referred to as. So in kind of a simple example, when two hydrogen 1s orbitals overlap, right, because hydrogen only has one valence electron, and so the 1s orbital is where their valence electron lies. When these two 1s orbitals overlap, two molecular orbitals result: a sigma bonding molecular orbital from constructive interaction, and a sigma antibonding orbital, like a sigma antibonding molecular orbital from destructive interaction, right? So in this example here, you can see that right, a 1s orbital from a hydrogen atomic orbital, or two of them rather, when they come together and they overlap, you have to form two molecular orbitals. You can't just make one, right? Because there are two atomic orbitals, so there must be two molecular orbitals. So what you see here is there's this sort of after this sort of overlap, there is a lower energy, right, indicated here by this relative energy bar. There's a lower energy sigma bond and a higher energy anti-bonding orbital. So the electrons, of course, will want to go, when these end up overlapping, they'll want to go into the lower lying molecular orbital, right? So in this case, essentially it kind of looks like this, right? Where you have your hydrogen-hydrogen bond, right? And the 1s orbitals, they can be positive or negatively phased, but either way you have one molecular orbital from constructive interaction and the anti-bonding orbital from destructive interaction. And you can see here, right, from the destructive interaction, they don't overlap. There's a node in between the positive and negative phases, and that is a indication there's no electron to be found there. And again, this vacant anti-bonding orbital kind of indicates that it does not play a role for neutral hydrogen gas. And so, of course, when two electrons go into the bonding molecular orbital with opposite spins, you form your stable hydrogen molecule. This is generally the case with most of the things we'll be talking about in this class, but in most stable molecules, all bonding orbitals are filled and anti-bonding orbitals are left vacant, for all intents and purposes as we're concerned in this class. So, I don't know if this here by accident, but that's a good reminder. We'll talk about now another example where we have two p orbitals coming together to form a pi bond. And I'm kind of going over these examples. We won't really talk about it too much in class. Again, it's kind of beyond the scope, but it is kind of important to understand how these bonds happen, right? So I won't be asking too many questions on this on an exam, for example. So when we have two unhybridized p orbitals overlapping, again, two molecular orbitals result. A pi bonding molecular orbital from constructive interaction and a pi anti-bonding molecular orbital from destructive interaction. So let's look at this example. So when you have the two pz orbitals coming together for two different carbons, right? So if we just had, for example, carbon-carbon double bond, right? Let's take a look. Let's take a look at what that would look like in the sort of MO diagram. Right, and we can kind of also illustrate what the pz orbital looks like. And because I have access to it, I will color these in. This will kind of be important to illustrate what the pi bond looks like. Right, so when these orbitals overlap and they come together, you form two MOs, you form the pi bond, and you form the pi anti-bond. And of course, the electrons come down to the lower lying molecular orbital, and the pi anti-bonding orbital remains vacant. So what does a pi bond look like when these orbitals come together, right? We saw it for the sigma bond, right, in the hydrogen example. What does it look like here? So let's draw it. And again, the blue and red, kind of like in the last example I showed, it's just kind of an indication of the phase of the orbital. So we could say like this is positive and this is negative, for example, but again does not indicate charge. So when you form the pi bond here, you're essentially, it looks like this, right? Where the phases constructively overlap with each other, right? And so if we were to sort of put that onto a carbon-carbon bond like we have up here, what that would look like is this, right? So you have a carbon-carbon bond, right? So this is just in the middle, right? This is just a sigma bond. But when we look at the pi bond, it looks like this, right? So even though it might look like, deceptively, with the pi bond overlapping, it might look like, for a double bond, we have one bond here and one bond here, but that's not really the case. A pi bond exists, as shown here, above and below the sigma bond, right? So there is not 4 electrons here, but there are just 2, right? So this is where the pi bond comes from, right? So hopefully that makes sense. And just show you what the anti-bonding orbital would look like, right? Because it comes from destructive interference as opposed to constructive interference. It's going to look something like this, where the lobes look like they're almost repelling each other, like so. And of course you have the node in the middle here, where there is no chance to find an electron, right? So hopefully that makes sense. Again, this won't be something I'll be going over too much. We'll be maybe talking about it here and there, but this is just sort of, just so you kind of have an understanding of how these atoms can come together to make sigma and pi bonds. We'll kind of be illustrating things using this pi bonding scheme, but I won't be asking you to draw out diagrams like this for the most part. So let's talk about now hybrid orbitals. I think you're probably a little familiar with this from general chemistry, but hybrid orbitals are for making complex orbitals where you're mixing the s and p atomic orbitals to make sp hybrid orbitals. And so hybrid orbitals separate the electron pairs widely in space and place more electron density in the bonding region between atoms than the s and p orbitals could on their own. So in general, when we're looking at a molecule and we're saying, okay, what is a hybridization of this atom, right? We can kind of look at this. And what this is kind of saying is, in general, for thinking about how many hybridized orbitals something has, you look at the number of attached atoms and the number of lone pairs, and that is the number of hybridized orbitals on that atom. So let's look at hydrogen cyanide down here as an example. Drawn like so. And so when we look at this carbon, right, it is attached to two atoms. There's no lone pairs, so it should have two hybridized orbitals, right? So it is sp hybridized. And so when we're looking at the nitrogen atom now, it is attached to one atom and it has one lone pair. So two things. So it has two hybridized orbitals. So it is sp hybridized. And of course, hydrogen here has no p orbitals, so there's no hybridization. There's no mixing going on because it just has that s orbital on its own. So what does this kind of look like, right, in terms of, let's look again at electron configuration, sort of see how this mixing actually happens. Right, so for carbon, let's just look at carbon for this example. If you remember, for its electron configuration, 2s, 2p, right, this is what it looks like. But when these orbitals have to mix and has to form bonds, right, it can't just do it like this, right, because look, in the 2s orbital, those two electrons are paired, and you don't expect them to be doing anything. But, in fact, they do. It can make up to 4 bonds. So what happens when these things mix, right? So when they mix, you end up forming this. Actually, hold on. You still have your 2p orbital, but now you have sp orbitals as well, and the electrons are filled in like this, right after that mixing. Mixing also changes the relative energy of the orbitals. So you see the sp orbitals are kind of higher in energy than the s orbitals, but the p orbitals remain the same. And these p orbitals, kind of importantly, are unhybridized, right? So the sp orbitals are doing the sigma bonding, and the two p orbitals are doing the pi bonding, right? Because see, carbon has a triple bond. There are two different pi orbitals, and that's where these, and that's where they come from these unhybridized p orbitals. And we'll talk about that a little more in a bit, and hopefully it'll make a little more sense visually then. So what do these sp orbitals look like, right? We know what an s orbital looks like. We know what a p orbital looks like. But what does the sp orbital itself actually look like? So let's look at carbon again. So with carbon, right, 2s, and it constructively interacts with a 2p orbital, right, when it mixes. And so when it does this, and I'm just going to shade one lobe here for positive and negative, instead of using colors. When it does this, going to forming an sp orbital, which looks like this. Right, and you can kind of see it takes on the appearance of the two orbitals combined, right? Because you have constructive interference from the white portion here and destructive interference from the shaded portion here. Right, so this is what the sp orbital looks like. And of course, because we have two atomic orbitals, there has to be an additional sp orbital. And what that looks like is just the other phased lobe, where we get the kind of opposite, quote unquote, sp orbital. And I'm going to redraw that because it does not look as good as the first one. So yes, so when you have two atomic orbitals coming together, you have two molecular orbitals that result, right? So, and these are what are forming, right, the sigma bonds, right? So the sp lobe here, right, with the constructive portion facing right, would essentially be the bond connecting nitrogen to carbon, and the other lobe here would be what's connecting the carbon to the hydrogen, right? And so, kind of as the notes say down here, we began with two atomic orbitals for carbon, so we must finish with two sp hybrid orbitals. And these hybridized orbitals provide enhanced electron density in the bonding region for a sigma bond towards the left and right of the atom. So I hope that makes sense. And again, this is like a little bit more detail than I might require you to know on like exam or homework, for example. I think it's good to go into this level of detail so you kind of get an understanding of what these orbitals look like, right? So let's look now at pi bonding. So pi bonding results from the overlap of two unhybridized p orbitals, oriented perpendicular to the sigma bond connecting the atoms. These orbitals overlap sideways with electron density above and below the sigma bond connecting the atoms, right? Kind of like we discussed a few slides ago with that drawing out of the pi bond. And kind of importantly here, while sigma bonds can rotate, the pi bonds cannot, right? Because they have that upper and lower orbital overlap, right? So they can't rotate without breaking that bond. So let's take a look at some examples of what pi bonds look like on various molecules. So let's look at this example here, where we have another example of double bonded carbon, right? So drawing with a Lewis structure. It might be important for you guys too, as we're kind of going through these, if you pause the video and try to draw out some of these Lewis structures before I get to it, it might be good practice on your own there. So what is the hybridization of each carbon, right? Again, hydrogen wouldn't be hybridized because it has no p orbitals to mix with, but carbon does. So what is the hybridization of these carbons? So for both of these carbons, actually, they are sp2 hybridized, right? Because they have three things they're each connected to, three atoms they're each connected to, and no lone pairs. So there's three hybrid orbitals, so sp2, right? So what does that pi bond look like visually? Let's take a look. So kind of like the previous example I showed you, we have that sigma bond here in the middle. And so for the pi bond, right, it's going to be over and under that carbon. Of course, we have the constructive overlap here of the pi bond from the unhybridized p orbitals, right? And that is where the electrons lie for the pi bond. I'm kind of just drawing in these differently spinned electrons just for you to see it. You don't have to draw them in yourself whenever you do this, but it's good to sort of keep track of, yes, you know, the electrons are here and here in a pi bond. We can even draw them on the sigma bonds too, just to get a better idea, right? So there's two electrons here in the sigma bond, and of course there are two electrons in each sigma bond here from that sp2 hybridized orbitals connecting everything together. right? And so what do these hybridized orbitals look like? So let's take another look. When we are thinking about these orbitals, we have to again start with the atomic orbitals that are actually mixing. So, 2s, two px, and 2py. So we can consider these orbitals here that are unhybridized as the 2pz orbitals. And I'm kind of drawing them in a certain way, right? Because they can't all exist in the same plane. You have one in the z direction, one in the y direction, and one in the x direction. But that's kind of arbitrary. So we have the differently colored lobes here. And because we have 3 atomic orbitals, when they all mix together, we should have 3 sp2 hybrid orbitals. And they'll look pretty similar to the sp orbital. They are different in size. There is a more p character to them, technically, because there are 2 more p orbitals mixing. But my drawing abilities probably will not be able to illustrate that super well. And right, so with these 3 p orbitals, they are technically in different directions. To form your 3 sp2 bonds, like so. Right, and again, 3 atomic orbitals, so we have to have 3 molecular orbitals as a result. Okay, so these are all sp2 hybridized molecular orbitals. And the pz orbital, the unhybridized one, is occupied in doing pi bonding with its carbon partner. So let's look at one more example of this. This time it'll be triple bonded carbon. So let's take a look at that. So let's draw out the Lewis structure. Right, kind of like the example of hydrogen cyanide, we know that this carbon is attached to 2 things, so it is sp hybridized, right? And same with this other one, sp hybridized. So what does that look like now? We know what the sp orbital looks like because we drew it out a little while ago. But what does the pi bond look like? Because it not just has 1 pi bond, but 2 pi bonds, right? And so that means, right, it's just because we know that there are 2 hybrid orbitals for sp, that means there are 2 unhybridized p orbitals that are available for pi bonding. So let's take a look. So I'm drawing only the sigma bonds here. And so what does the triple bond look like in sort of molecular orbital fashion? So we have the one we've drawn several times now, but we also have one in a different direction, right? So this one, we can, let's say it's pz, it's in the z plane, but we have to draw another one, and that's going to be on the x plane. It's going to look like this. Hopefully once I color everything in, it'll visually make more sense, be a little more appealing. Drawing in the different phase lobes. So now what happens is these orbitals are, right, they are constructively interacting, right? So that's what's forming these pi bonds here. So you have constructive interaction here. Above, below, and kind of on the sides now. of this carbon-carbon sigma bond. So that is where the triple bond is coming from, right? From the PZ lobe here, and then another from the PX lobe here, right in the X plane. So you have two different unhybridized p orbitals forming pi bonds between the two different carbon atoms, right? So I hope that makes sense. From a Lewis structure standpoint, this looks pretty simple, but here, things aren't as linear as it might seem. So hopefully that makes sense. And I would encourage you to make sure you can practice drawing out these Lewis structures and recognize their hybridization. Make sure you have a good grasp on what these p orbitals look like, and when they form pi orbitals, how do they look like?